Okay, so in this lecture video, we're going to talk about how a process flow for a MEMS device looks like. And then we talk about some of the constraints. The issue is that, what we want to figure out is that how do you put together the steps that we learned so far? The deposition techniques, doping techniques, maybe thermal oxidation, photolithography, and etching steps. How do we arrange them such that we get the desired geometry for our MEMS device? So this is called process integration, right? So how do you put together these processing steps to get the desired outcome, noting that once you do a process, you will add new constraints to your subsequent steps. So for example, if I put down a layer of silicon nitride on my wafer at the very beginning, I can never have thermal oxidation anywhere in future because I do not have access to the surface of that oxide, that silicon anymore. If I have a layer of aluminum on my wafer, I cannot have any processing steps that require temperatures above, let's say, 500 degrees Celsius because it's going to affect the aluminum that I already have on the wafer. So, how do we do this? How do we come up with a new process flow is the subject of process integration. It's called process integration. While we go through these, the process engineer, the vendor that provides the service to you, will give you a set of design rules that you have to stick to. In some cases, they will not manufacture your device if design rules are violated. And in other cases, they will not guarantee any performance if design rules are violated. What these design rules tell you, especially as a MEMS engineer, is that, so let's say they say, I cannot have a gap of less than 2 microns in my process. So if in your layout you have two structures that are separated by 1 micron from each other, let's say by mistake, when you were drawing it, it just moved by 1 micron, there's a very good chance that they will be stuck together when the process is finished, right? Or similar things. So they say the minimum line width is this much, the minimum gap is this much, the maximum dimension in some cases is this much, and that's because they want to make sure that the process is repeatable. Because of the complexities involved, these are mostly empirical rules, design rules, and they're often tool dependent. So if you go to this manufacturer, they give you one set of design rules. If you go to a different manufacturer for a process that at the end looks like it delivers the same performance, they may have a different set of rules because they're using a different set of equipment probably. And maybe even the order of the processes is different. And for a MEMS designer, this is where the limits on the geometries, gaps, dimensions, the width of the lines, the different aspects, overlap between layers, the separation between layers, all of those are basically determined from this set of design rules. When you are developing a process, when you're designing a process, there's numerous considerations. The first one, and often one of the most critical ones, is thermal compatibility. If you have something that is temperature sensitive, you want to make sure that the subsequent steps do not raise the temperature beyond whatever that you can tolerate now. So for example, if you have had implantation to define doped regions and you want the dopants to stay where they are, you cannot have a process at 1,000 degrees later on. Because if that process 10 steps down the line happens to be run at 1,000 degrees Celsius, the dopants that you diffused or implanted right at this stage at the very beginning are going to start to diffuse sideways. They're not going to be where they are. They may actually mess up the entire process. Material is another issue, right? So will your material survive the higher temperatures? The other issue is that material property control. Can you get the stress that you want in that film? In most cases, we do not want to have compressive stress in the films because it results in buckling of the film or having those ripples that you saw before in the film. That's one thing, but also electrical properties of the film are important in many cases. Optical properties, if you're making a micro-opto-electromechanical system, are important. And you again want to make sure that whatever you do now is compatible with what you will have later on or what you had before this point. Mechanical stability in most cases goes back to the stress control in the film, but also, can you have a wet etching step at this point? Or you may cause stiction of the layers if you have a wet etching step. Device geometry, especially in case of anisotropic etchants, wet anisotropic etchants, how can you get the geometry that you want in this process? If you have to have corner compensation shapes or attachments, they work only for a limited range of depths and etch rates. So make sure that those are steps. Order of steps is very important, right? So if you go back in CMOS manufacturing, for example, as a familiar example, in the early days, you created the drain and source of the terminal first, then put down the dielectric for the gate, and then put gate material, usually a layer of, let's say, aluminum on top of that. Well, as the processes got more and more complex, as we started to reduce the distance between drain and source, that process turned out to be less, let's say, suitable for scaling. And instead of having the gate last process, as I mentioned, that we made the gate last, now they have a gate first process where they go and deposit the gate dielectric, put the gate electrode down, then they create the openings to drain and source and do the implantation to create those two. And this way they can actually make smaller features. At the end of the story, when you look at the cross section, it's the same thing, but you have switched the order of the processing steps because of advantages that sometimes are not too obvious. Do you have backside processing? In microelectronics, no, but in MEMS, sometimes you have features on the other side, on the backside of the wafer. And so on and so forth, right? So there's just a lot of considerations when you design a process flow. You basically have to know what your facility is capable of doing. You have to know what you want on your wafer at the end, and you have to go and figure out what process in your facility can, maybe you have 3 ways of etching. You can do wet etching, we can do RIE, you can use DRIE. Maybe you have different ways of depositing your film. You can have sputtering, you can have evaporation, you can have CVD for that, let's say, particular film that you're interested in. Which one do you choose? How do you put them together? And the order and sequence of these processes is going to be very, very important. So it's not a simple task. It usually is done by experienced people. And because the process is so, let's say, challenging to develop, usually they don't let you modify it. If it is a big manufacturer, they don't let you modify it in any way. They don't want to mess up any of the parts of that complex system that is working for them at this point. If you are a student or a researcher and doing it for your own work, you have to go and figure out all those things on your own, and it usually is a time-consuming process. So let's look at one commercial process. It's called SOI-MUMPS. You can still order chips in this process. You can send your layout to the company, MEMSCAP, and they have a set of design rules. You can just download the design rule handbook from the web and have a look at it. If you stick to their design rules, they will make the chip according to your layout and send it back to you. So this is a foundry that is providing manufacturing service to others. But in this case, you do not have any option to move the process or to modify the process in any way. This is what it is. You fit to that process. You fit your design to this process. It's a bulk micromachining process. You start with an SOI wafer. The thickness of your structures can be 10 or 25 microns. This is the only option that you have. They can start with a 10 micron wafer, 10 micron silicon layer, or 25, but the rest of the steps, they do not change for anybody. So here is a cross-section of the structure at the end of the story. What you can see here is that there is a handle wafer, this blue region. There is a buried oxide layer, the black region here. Top device layer, this silicon layer that is 10 or 25. The red one here. You have gold or metal on top of silicon here, but you also can have metal here. Obviously, these are not deposited at the same time. And we'll talk about the design flow for that in a second. One other thing is that you can see that the handle wafer is etched. There is an opening. This is where your device is. So the device is basically sitting on top of a trench, and the buried oxide underneath the device is removed. So let's see how we can do this. So as I said, if you just type SOI-MUMPS in your search engine and download the handbook, all these steps are described in more detail over there. But what they want is, what I'm going to show you is quickly the order of processing steps here. This is a fairly simple process for manufacturing the devices. So this is the ultimate goal. This is where we want to be, and this is where we start. So you start with an SOI wafer that has a little bit of oxide on the backside. You coat it with a photoresist, with a PSG dopant here, and you dope the top silicon wafer, the silicon layer, through that PSG, photosilicate glass. The reason is that you want to lower the resistivity of that layer. So that's the first step in your process. You take an SOI wafer, there is an oxide layer on the back side, and the top side you just go and dope it so that the resistivity is lower across the entire surface. The next step is that you get rid of the dopant here. In that case, it was a constant number of dopants at the surface. So once you're done with doping, you remove that glass layer, and you go and deposit your first film. And this is a metal layer that you use for, let's say, improving the electrical conductivity across different sections on your chip. After that, you go and pattern the device layer. This is done by a DRIE step. So each one of them now has its own mask, right? So the first mask is for metal layer. Let's call it metal 1. The second mask is device layer. And once you're at this stage, you flip the wafer over, protect whatever you had on the surface, and etch the handle wafer. So you create an opening from the back side of your wafer underneath your device. You remove the silicon first, and then the oxide that was underneath that device layer. So you remove the silicon through a DRIE step, and then the black oxide is removed afterwards. So now your device is basically hanging. There is a protection that you have from the top side, which you remove in the next step, and then you use a shadow mask to deposit additional metal on these structures. Shadow mask is basically you put a plate with openings in them, with holes in it, and you put it right on top of your chip. You evaporate metal through those holes onto your chip. So without using a mask, without doing lithography here, you can have metal on your chip. Process is easy. The challenge is creating the shadow mask itself. But once you have it, it's basically very easy to do this step. The reason that we are doing this deposition through a shadow mask is that they want to have metal on the top of this device layer as well as the handle wafer here. And you cannot do that with regular deposition and etch, deposition lithography and etch sequences we have because of the height difference here. Obviously, because you're using a shadow mask and none of those more advanced lithography techniques, your resolution is not that good, and it shows in the documentation for the process, but you now have electrically access to the handle wafer. So here is a summary of the design rules for the process that you can see in the handbook. So for example, what they say is that the SOI layer, the minimum feature size is 2 microns, and the minimum spacing between the features should be 2 microns. Basically, you cannot have a gap smaller than 2 microns, or you cannot have a beam that is narrower than 2 microns. That's what it means. The maximum feature length is unlimited if the beam is wide enough, 6 microns or longer, but there is a limitation on it, because if a beam is too long and too narrow, it just becomes too flexible and it breaks during the process. Hole is what you have inside the silicon layer. It's the same layer. They give it a different mask, a different layer name, but it's actually merged with SOI. So you actually have more or less similar design rules for it. Trench is what you have on the back side. So it's a crude etch. The minimum feature size is 200 microns. So it's fairly large, compared to 2 microns that you have for silicon on top. You have 200 at the back. And the maximum feature length is 5,000 microns. So it cannot be larger than 5 millimeters. That's for mechanical stability of the entire wafer. Blanket metal, the one that you use, you deposit through the shadow mask. You can see that the minimum feature size is 100 microns. The first metal layer that you deposited is 3 microns. That's the layer that you deposited using deposition, lithography, and etch. This one is where you use the shadow mask, and your limitation is about 100 microns. So anyway, as a MEMS engineer, I probably don't, it's best if I know how the processes are done, and I'm basically have enough education to figure out the limitations of these processes. But what I can work with is this table of design rules. And then what I go and do is that I design making sure that my device doesn't violate any of these design rules. So this is the layout of my device. At the end of the story, I go and make sure that everything is where it is supposed to be. These are the layers in my layout that I can basically turn on and off in order to focus on certain regions. I created 3D structure out of the layout in addition to the process flow parameters that I have. So this is a top view, bottom view. I have created the trench that goes all the way to the bottom of the device. And side view is like this. You can see that everything is happening at the top, let's say 25 microns of this wafer, and the rest of it is just handle wafer. And then if everything goes well, I can have this fabricated, and then this is what I get back from the company. According to let's say this design layout here, after I do all the simulations and everything else, this is the device that I get back from the manufacturer. And these are some examples of devices that our group has made in SOI-MUMPS technology. Now, the next process is a PolyMUMPS process. It's a very old established process, still around. It's a surface micromachining process. What it does is it gives you access to 2 structural layers. So there's a polysilicon layer that is about 2 microns thick, another layer on top of that that is 1.5 microns thick. You can have these layers on top of each other, so you get a 3.5 micron thick structure, or you can have them separated from each other through a sacrificial oxide layer that separates them from each other. You also have a polysilicon layer that is highly doped and is on the surface of the wafer for electrical connections. It's a surface micromachining process. All these layers are relatively thin, and please have a look at the slides that we have for this. I have gone through the entire steps, the major ones. There is a lot of details here that we probably didn't cover, but you can go and check the design manual if you're more interested. And again, you can see that it's a more complex process. You have a larger set of design rules, and now you have design rules for the overlap between layers and the separation between layers, as well as each layer. And these are samples of devices that were made in a PolyMUMPS process in the past in our group. And then this one is especially interesting because actually if you zoom in, this is a polysilicon layer, this is poly 2 layer. You can actually see the polycrystalline structure of the film. You can see the tiny crystals that are packed together to form that polycrystalline film. And then the last example here in these slides is a bulk micromachining process called the screen. It's a fairly simple process. What we do is that we go and etch a substrate through a dielectric layer, and then take advantage of what we know of the process. So we know that isotropic processes, let's say, go sideways as well as downwards, and DRI just goes downwards straight. And then if you do metallization, let's say through evaporation, you cover the sidewalls less than the flat areas. And just have a look at this screen process. If you have questions, just try to figure out how it works. There is a reference to it. I can put it on the website so that you can go and check. It's a very simple process. With one mask, you can actually create a MEMS device out of a simple wafer. Finally, we have some examples of packaging. So in this case, wafer level packaging, where we go and cover the material with a sacrificial dielectric layer, then deposit our, let's say, whatever material that is going to protect our wafer from from our device from, let's say, mechanical impact or whatever. It could be usually a layer of, for example, nickel or a thick layer of polysilicon. Then we remove the sacrificial dielectric that we had here through openings in that film and plug that film. And by plugging that film, what we mean is that we do a little bit of CVD or sputtering to basically close down that opening here. And then what we have here is a hermetic chamber for our device to basically be operating and be safe from the environment. An alternative is wafer level packaging through bonding, where you again make your device here but create a cavity in the second wafer, bond these two to each other through one of those bonding techniques that we mentioned before. In this case it's eutectic bonding, but all sorts of bonding techniques may be used here. In both cases of wafer level bonding, the challenge you have is basically making sure that you have electrical connections to the device that is inside that hermetically sealed chamber. And then finally, once you have packaged your device and protected it through wafer bonding, you go and do a wire bonding. You basically make contact to your MEMS device, MEMS chip inside the package to the pads on the package. It's a fairly simple process. You just go from a pad on your MEMS device or microelectronic chip, press your gold wire or aluminum wire at one end, and then go and make a connection to the other end and cut it off through electrostatic or heat energies. Ultrasonic or heat. Here is an example of making a straight beam. We saw this before. I would go through the manufacturing steps here during a live session in our course, but that is basically our topic, our discussion for MEMS manufacturing. We have one example of how to design a process based on the requirement for a MEMS device. Again, I will cover this during our live sessions if you want. So we try to come up with a set of processing steps and rules for making a given device. In most cases, we have a process and we have to design the device according to the process requirements. In this case, I'm going to say, okay, you have all the freedom that you want. This is the device, go and design the process based on it. So we go through that in the live session as well. So that's it for the microfabrication section of the course. And then the next topic that we will be dealing with is micromechanics. Thank you.